Okay, we will now start with section number 3, known as our bias exercise time. Throughout the course, as we complete chapters, there will be exercise sections where we will show you how the exercise is structured, we will answer it together, and there will also be a couple of pauses in case you want to try and do the exercise on your own. Okay? Now, please note, and we added here in the disclaimer, that this work will use fictitious names to make exercises relatable to students. Names, characters, places, and incidents either are products of my imagination or are used fictitiously. Any resemblance to actual events or locales or persons living or dead is entirely coincidental. Okay, so we're adding names here just to make it a little bit more fun, but we do not imply any type of statement regarding these companies. Okay, so exercise number 1 is known as Metrinico. So Metrinico is testing out a new measurement system that uses a caliper for a length measurement. Before implementing the new caliper, we must determine that the results provided by the caliper are accurate and do not introduce bias into the measurement result. To do this, Metrinico takes a 3.5-inch gauge block and measures the gauge block exactly 10 times with the same inspector. The results are summarized below. Is the system introducing bias to the result? So here we can see Roberto, which is our inspector. He has been provided with caliper EN015, and he has measured a 3.5-inch gauge block 10 times. The output is right here. As you can see closely, sometimes he's saying that the gauge block is smaller than 3.5, sometimes he's saying that it is bigger, and sometimes he's saying that it is exactly 3.5. This is normal when you're measuring. Sometimes you will say parts are a little bit smaller, sometimes a little bit bigger. The point is that on average, you do not say that the parts are always smaller or that the parts are always bigger. So test for bias, we're going to do our one sample t-test analysis. So I'm simply going to copy the information and paste it here into Minitab. After copying and pasting my information, I can now do stat, basic, and one sample t-test. I'm going to select the column that contains my raw data, which in this case is C3. And here I'm going to do a hypothesis test. My hypothesis test is what the gauge block actually measures, which in this case is 3.5. I will now click on the OK option and I will review my output. Please take a moment to think about the output. Based on what we covered during section 2, do you believe the system is introducing bias? Is it reporting the parts as being smaller or bigger than they actually are? I will take a short 2-second pause. You can pause the video right now as well. And then I will provide the answer. Okay, so here we look closely. You're going to notice that I have my mean right here. The mean has been calculated as being 3.497. 3.497 is clearly smaller than 3.50. However, there is a confidence interval. The confidence interval goes from 3.493 to 3.51. You might notice that the value of 3.50 does fit within this range. As such, we conclude that the system does not introduce any bias. It is not underreporting or overreporting parts, so the system should be fine. We can also confirm it again with our p-value. Since the p-value right now is above 0.05, that means that there is no bias introduced into the system. The different results that I'm getting are simply normal variation from when you're measuring a part. Sometimes, even if you have the exact same part and you have the exact same operator, the operator is going to close the clamps a little bit more, it's going to close them a little bit less. It is not the measurement system's fault. Okay? Such, this system, what we would do on our exercise sheet is we can do a right click, copy as picture. I'm going to paste the information here. I'm going to do again a right click, copy as picture. I'm going to paste the information here. And I'm going to say the system does not introduce any bias since the p-value is above 0.05. Okay? This is how we mathematically and statistically demonstrate to an auditor that our measurement system is properly calibrated and is not underreporting or overreporting parts. We simply do measurements and we output a hypothesis test for the mean of those measurements. Now, we're going to look at exercise number 2. Medtrinic has now purchased a new CMM machine and wants to determine that the system is properly calibrated. They take a 2.5-inch gauge block and measure it 15 times with the CMM touch probe system. The results are summarized below with 4 decimal places of precision. Is the system introducing bias to the results? Take a moment to try and do this exercise on your own, based on the information we have supplied so far. You can pause the video right now, and I will provide the answer in a couple of seconds. Okay, so we're simply gonna copy our information. Gonna copy this. Gonna paste it on a brand new worksheet. There we go. And then we're gonna do stat, base statistics, and then we can simply do one sample t-test. I'm gonna grab the column that has my output, which in this case is C3, and I'm gonna do the hypothesis test, and I'm gonna say it's a 2.5-inch gauge block. I'll click on the OK option, and I'll review my output. Take note that I keep clicking here. It's a nice, easy way to switch out. You can also simply drag this to make it a little bit smaller and help you guys see, but it's easier to just click here. Okay, so I'm gonna copy my output. I have my output right here. There we go. I'm gonna copy this as well, and we can paste it. Based on the output, is there any inherent bias, yes or no? Just by looking at my mean, I can see that the mean is 2.5, and then we have 8 10,000ths, right? So it's really close to 2.5. Now, is there a bias or is there no bias? Well, I can look at the confidence interval. The confidence interval right now goes from 2.499 all the way over to 2.50. The value 2.5 exists within this range. As such, the hypothesis test will pass. I can also confirm it with my p-value. Center is above about 0.05. There is no bias on the measurement system. So I'm going to add that output here. There is no bias in the measurement system since the p-value is above 0.05. Remember that if you're struggling with any of the conclusions so far, don't worry. As we do additional exercises, it will start to make more and more sense. Okay? Our Consumer Academy courses are structured in such a way that we continually challenge our students. So if you don't feel challenged, then the course is simply too easy. Now, let's look at exercise number 3. Medtrinic has been having issues with inspectors reporting parts as out of spec at random points during the day. One of the possible root causes is that one or more of the 5 calipers that are currently being used in the shop floor are not properly calibrated. To test this, all 5 calipers have been used to measure a 5-inch gauge block 10 times with the same inspector. We use the same inspector to avoid introducing additional variation. The results are shown below. Are any of the calipers introducing bias? So we grab our trusty inspector Carlos, and we ask Carlos, please grab this 5-inch gauge block. You're going to measure it 10 times with caliper 1, 10 times with caliper 2, 10 times with caliper 3, and so on and so forth until we can determine if any of the calipers are introducing bias. So I can grab my data and I can copy and paste it over into Minitab. You can pause the video right now if you would like to do this exercise on your own, or just give me a couple of seconds and I will provide the answer. Okay, so over here we're simply going to do stat basic one sample t-test, and we can do C3, C4, C5, C6, and C7. We're going to add 5 inches for the hypothesized mean, and we simply execute our study. The output is going to be provided here. I'm going to copy it as a picture. I'm going to paste it here, and I'm going to copy the test results as a picture, and I'm going to paste them right here. So just looking at the low-level data, I can see that caliper 1 has a p-value above 0.05. So caliper 1 is fine. It has no bias. Caliper 2 is also above 0.05. So again, caliper 2 introduces no bias. Caliper 3 is actually below 0.05. So it does introduce bias. Caliper 4 above 0.05 does not make any bias. And caliper 5 is below 0.05. It does introduce bias. Please take note that the one sample t-test does not tell me if the bias is positive, as in we report parts as being bigger than they are, or negative, as in we report parts as being smaller than they are. To determine that, I need to look at the low-level data. So I know that caliper 3 and caliper 5 are bad. If I look at caliper 3, I know that the gauge block is 5 inches, but caliper 3 reported the mean as 4.979, with the confidence interval going from 4.97 to 4.98. So caliper 3 on average will report parts as being 0.02 inches smaller than they actually are. Caliper 5 is at 4.96 with a confidence interval between 495 and 496. So caliper 5 will report parts as being smaller, for 0.04 units smaller than they actually are. Here I can identify no caliper that is over-reporting parts. So what should we do as quality engineers? Well, we should take caliper 3 and caliper 5 out of rotation until we calibrate them. Here we can state calipers 1, 2, 4, and 4 are properly calibrated and do not introduce any bias. Calipers 3 and 5 should be taken to the calibration room for inspection. They have p-values below 0.05. Let's look at exercise number 4. After identifying the root cause from the previous exercise, Medtronico sent all calipers out for calibration. A follow-up study was executed to determine if the bias remained. The results are shown below using a 5-inch gauge block. Do any of the calipers introduce bias? So again, we're using Carlos. We provide him with the 5-inch gauge blocks, and we measure 10 times with each individual caliper. You can pause the video right now to try and do the exercise on your own, or just give me 2 seconds and I will provide you with the answer. Okay, so I'm gonna copy the information here. There we go. And I'm gonna do the same thing I did before. Stat basic 1 sample t-test. And I'm gonna select the columns that have the calipers. Please note that if my data is structured in this way, for example, C3 to C7, I can also just type in C3-C7 and Minitab will understand that it needs to do the test for each individual column. You could have also simply highlighted and click on the select option, and that will also add them over for analysis. So I will click on the OK option, and we're going to copy as picture our output. So we have one section, and we have a second section. And now we simply look at our p-values. Caliper 1 is above 0.05, so no bias. Caliper 2 above 0.05, no bias. Caliper 3, Caliper 4, and Caliper 5. There is no bias introduced into the system. Now, having no bias does not mean that their mean is exactly 5, as you can see right here. It simply means that the value of 5 is within the confidence interval calculated for the population mean. So here in the answer section, we can state all calipers are properly calibrated and do not introduce any bias. All p-values above 0.05. Okay, You can also conclude based on the confidence interval, but in statistics, it's a lot easier to just look at the p-value. For people asking what is a p-value, it is a way for statisticians to actually know if the hypothesis test that we are doing is going to pass or is going to fail. We must always look at what is our null hypothesis and what is our alternative hypothesis. In this scenario, the null is that the mean is exactly 5, and the alternative is that it is different. It can either be higher or lower. To determine if it was higher or lower is when we must actually look at the low-level data and conclude based on it. Now we have an on-your-own exercise. The purpose of an on-your-own exercise is for you to do it all on your own. The previous exercises, you could have done them on your own if you wanted to, but this one, please try and do it without any assistance. So for exercise 5, we have on your own exercises are intended to be done without looking at the instructor for help. They should take less than 2 minutes to complete. If you're struggling, please just wait and we will provide you with the answer shortly. The question is the following. Jobil is a medical device company that is analyzing its current measurement system for length measurements using a caliper. To determine if the system is properly calibrated, the following 3 calipers have been tested, measuring a 0.5-inch gauge block. Determine which, if any, of the calipers have bias. If there is bias, determine if the bias is toward reporting parts as being smaller or bigger than they actually are. So we grab Raphael and we ask Raphael to measure this 0.5-inch gauge block with 3 different calipers. Please do your best right now to determine if we should decide that all calipers are properly calibrated or if one or more calipers are biased. If you identify a caliper as being biased, please report if the bias is towards saying that the parts are smaller or towards saying that the parts are bigger than they actually are. Okay, so if you didn't pause the video right now, or if you're just returning, I will now provide you with the answer. Simply, we do stat basic one sample t-test, and we can do C3 to C7. Oh, sorry, C3 to C5. Our hypothesis is that the gauge block measures 0.5 inches exactly, and we click on the OK option. We now simply copy our output, and we can paste it right here. So we have descriptive, and we have our test statistics. There you go. Based on the output, which caliper right now is biased? Is it caliper 1, 2, or 3? Just by looking at the data, we can tell that caliper 1 is correct, it is above 0.05. Caliper 2 is also correct, above 0.05. And caliper 3 is biased at being below 0.05. The question is if caliper 3 underreports or overreports. So if I look at the mean here, I can see 0.49. If I look at the data for the confidence interval, it can be as bad as reporting as 0.483 or as good as reporting as 0.498. Either way, it is underreporting. It is a negative bias. Report small parts as being smaller than they actually are. So here in the answer section, we're going to state caliper 3 is biased. Its p-value is below 0.05 and it underreports parts. It reports parts as being smaller than they actually are. Okay. Example 6 and example 7, or likewise exercise 6 and exercise 7, are again intended to be on your own exercises. Let's start with exercise number 6. Jobil is testing 4 CMM machines for proper calibration. We currently have a 2-inch gauge block for testing. How many inspections would you recommend and how many operators do you need for the test? Please think about it and we'll provide the answer in a couple of seconds. Okay, so if we have 4 CMM machines, I'm gonna draw them here. So we have 4 CMM machines, right? So machine 1, machine 2, machine 3, and machine 4. We have a 2-inch gauge block, so that's going to be the sample that we're going to be using, a 2-inch block. How many inspections will we do? We recommend best practice to be 10 inspections per machine. Okay, so we would have a total of 40 inspections. Now you can always do more than 10 or you can do less than 10, but 10 tends to be a good best practice. There is no international regulation that will tell you need to do 12, you need to do 15. If you're not doing 5, you're wrong. It doesn't work that way. But as a best practice and recommendation from Kusum Academy, 10 should be more than fine. Okay. Now, how many operators do we need? We want to avoid introducing bias to the study by mixing and matching operators. Let's say, for example, Carlos likes to put the sample here on the machine, while Luis likes to put the sample here on the machine. We know that there shouldn't be an impact, but we want to make sure that all machines are being inspected exactly the same configuration, same part routine, and same inspector, because we're testing for bias on the machine, on the measurement system itself. Okay. When we test for the impact caused by changing between Carlos, Luis, Andres, Nancy, Michelle, etc., we're now no longer talking about a bias study. We're talking about a gauge R&R type study, which we will cover later on. So the first step in any MSA is to prove that the system is not biased. Once you can prove that the system is not biased, we can swap over to testing that it is not influenced by who uses it. So here we would say in total that we need 40 measurements and only 1 inspector. Okay. Now, Jovial has executed the bias study for the 4 CMM machines using a 6-inch gauge block. The results are shown below. Determine if any of the CMM machines are biased. Again, please try and do this exercise on your own. By this point, you should already be familiar with the flow that we're following, which is stat, statistics, and 1 sample t-test. You can pause the video right now or just wait a couple of seconds and I will provide you with the answer. Okay, so let's copy our table. So I'm going to copy this right here. There we go. And paste it here. We're going to do stat, basic, and 1 sample t-test. A neat little trick that you can always do with Minitab is Control plus E. Control plus E will repeat your previous command. So if I do Control plus E, I have 1 sample t-test already ready to go. I don't even need to look it up. Okay. Now we're going to select our C3, C4, C5, and C6 columns. And our hypothesized mean is 6 inches. So I'm going to type in 6. I will now click on the OK option and I will review my output. I can copy the information as a picture and I can paste it over here into my file. So let's grab this and let's grab this as well. And we can paste it. Reviewing the data that I get, I can see that CMM machine 1 is below 0.05, so there is bias. CMM 2 is above 0.05, so no bias. CMM machine 3 is very close, but it is still above 0.05, so no bias. And CMM 4 is above 0.05. So no bias. Next follow-up question is if the bias from CMM machine 1 is positive or negative. To test that out, I will now review the data that I get here. I can see that it is at 5.9999998. The confidence interval goes from 5.99 all the way to 5.99997. The value of 6 does not exist within this range. As such, CMM machine 1 is biased. It is biased toward reporting parts as being smaller than they actually are. which is in contrast to CMMs 2, 3, and 4. So here we can state CMM machine 1 is biased and reports parts as being smaller than they actually are. P-value below 0.05. Okay. Now, some of you guys might be asking yourself, well, wait, I'm measuring a 6-inch gauge block. The mean is 5.9999. The confidence interval is so close to 6. Should I still say that the system is biased? I mean, it feels a little extreme, right? So in section number 4, which is going to be our next lesson, we're going to talk about when bias is significant in terms of our actual measurements. For example, if I have this particular CMM machine that reports parts as being 1/10,000 of an inch smaller than they actually are, but I have a spec that is plus minus 5 inches, well, it doesn't really matter if I use CMM machine 1, 2, 3, or 4, right? So there needs to be a criteria for determining if I should use the machine or not based on what I'm trying to measure with the machine. Okay, so mathematically or statistically, a system can be biased, yes, but in section 4 of this Word document, we will cover when we should actually worry about it. Stay tuned.